convolution sum and some of examples which are related to discrete time signal and discrete time system. Now let us focus on continuous time system, and of course the input is continuous time signal. So I am going to consider first let me discuss impulse response for continuous time systems. For this I am going to consider linear time invariant continuous time system. Okay, now the input is not an arbitrary input, let us say del of t, continuous time impulse. Okay, and the corresponding output is denoted by h of t. What is h of t? Impulse response, the response due to impulse. That means what? The response or output due to the impulse at the input of the LTI system. Okay. And we also assume that in our discussion this is a system with the zero initial condition. Why? If it has some non-zero initial condition, then the linearity will be destroyed. Okay, that means what? Assume that it has no initial conditions on the capacitors and inductors. That means stored charges in the capacitors and stored flux in the inductors. Okay, therefore the system is the system zero initial stored energy is 0. The reason is we are going to apply the principle of superposition, otherwise you cannot apply the superposition. So how do you represent del of t? Del of t is an impulse like this. You put 1 and this 1 indicates not strength, it is the area under the pulse. If we enlarge it, the pulse exists from, let us say, 0 minus to 0 plus, and this center point is 0. So the width is roughly very small. Okay, so and whenever a number of excitations are present simultaneously, the responses could be superposed only if the system does not have any initial stored energy. Therefore we assume that there is no initially stored energy. If it has some initially stored energy or some independent voltage source or current source, then the superposition principle is violated. Now the output is, let us say, some arbitrary output, let me say like this. This is my h of t. So you are giving only one pulse, but the system produces this kind of waveform in the output. Just for representation purpose I have drawn this waveform, not necessarily every system should produce this kind of waveforms. Now the same system you take, now in short form let me put a CT system, continuous time, let us say LTI system. Now instead of del of t, you apply an arbitrary input x of t, okay, as an input. Okay, this is the general input or some arbitrary input whichever you have at your hand. Okay, let us say my general input is like this, something like this. Maybe it can represent a speech signal or music signal or voice signal. Now what you do, you can consider a small narrow section here. So let me consider a small narrow section like this. Let me enlarge so that it will be very easy to visualize. This is T, right? X of T, and this one is the width, let's say delta tau. So this is a narrow section of time, and this area can be replaced by an equivalent impulse. Okay. So here this region I can approximately treat as constant. Okay, this height is called x of tau. Suppose you have a function like this, let's say y of t is equal to t. You fix a point, let's say t is equal to 1, then what is the value? This value is, when you substitute t is equal to 1, then y of t becomes y of 1, right? Similarly, the center point is, let's say tau y. Therefore, this magnitude is going to be x of tau. That's what I have written there. So if we regard this an impulse, the impulse will have essentially the same area as this narrow strip, and the area of the narrow strip will be del of tau, that is width. Area is what is the formula for area? Area is equal to width times height. Now what is the height here? Height is this one. This is my height. That height is x of tau. And what is the width? Width is delta tau. Right? So this is x of tau times delta tau. This is the area of the impulse. And this one is the magnitude of the impulse, and that impulse is located at t is equal to tau y. So provided that you make these slices thinner and thinner, that means what? Delta tau goes to 0. Thinner and thinner means you make the interval length as small as possible. Then the approximation will be much more accurate. Okay, here we assumed this is constant, right? If you look at here, actually this is not constant, actually it is slightly bending. If you take a curve like this, if you slice, then there is maybe I can take here. If you take this interval, this is not constant, it is changing. But what we will do, we will approximate this is constant like this. But on the other hand, you take this length is very, very, very thin, then it is approximately constant. This one is approximately constant. So therefore, when delta tau goes to 0, then the approximation will be very, very accurate. So x of t can be approximated as number of impulses. See, you have x of t like this, you can take one impulse here, second impulse here, third impulse here, fourth impulse here, like that. Okay, so this is tau y plus delta y, and this point is tau y plus 2 delta y, like this. So there are number of impulses. A particular impulse which I have sketched in the in this figure, or here we have sketched only one pulse. So you have a function like this, you take very small interval, and the center point is tau y, and the width is delta tau, don't put tau y, delta tau, just for the simplicity. And this height in this region, this height is roughly what we are saying, x of tau. Let's say the average you take it, because this value is some value and this one is something. You take the average of this and this. Let's say this is value 1 and this is value 2, and take the average of that. Value 1 plus value 2 by 2, which is equal to x of tau y. Probably you will be studying these things in your mathematics course, especially numerical integration. Therefore, as I said, x of tau y times delta tau is the area under the curve. Under the curve, that is the magnitude of the impulse. So what is the area? The area is this one, like that, and the impulse is situated at the center point. So this is the location of the impulse. We put a arrow mark like this. That impulse is delta of tau y. And what is this point? This point is tau y. If the impulse is situated at t equals 0, then you write del of t. If the impulse is situated at some other location, let's say t naught, then you write this impulse by del of t minus t naught, right? Similarly, here this impulse is located at tau y, therefore this is denoted by t minus tau y. Therefore, roughly you can write that this impulse you can write as the area. What is the area? X of tau y times delta tau multiplied by, where is it? This guy is located. It is located at del of t minus tau y. So in your x of t, there are several such impulses starting from the whole duration. Let's say your speech starts at this time, let's say 6 o'clock 12 minutes, then you start to speak, then this is your speech signal. Now you have number of impulses like this. There are hundreds of impulses. So you need to add all the impulses. Then roughly you can reconstruct your x of t. This is your x of t. So x of t contains hundreds of impulses. You sum all the impulses. Let's say impulse 1, impulse 2, impulse 3, impulse 4, impulse 5, 6, 7, 8, 9, 10, 11, 12 and so on. There are many impulses. So you sum them up, all the impulses, then you will get a x of t. Therefore, summation of x of tau y times delta tau. What is this? This is the area of each impulse, each pulse. And these pulses are shifted in time, t minus tau y. So this is approximately equal to, it's not exactly equal, approximately equal to x of t. Therefore, x of t can be regarded as summation of several impulses, many impulses. So that means your x of t is now being regarded as many impulses. So if you want to find out the response to this arbitrary input, you take first impulse, find out the response. Response 1, let us say. Apply second impulse, find out the response 2. Apply the third input, apply the response. You got the response 3, like that. So finally what you do is you add all these guys and find the response. That response equal to sum of this response. Summation of response 1 plus response 2, output 2, output 3 and so on and so forth. So you add them up. Okay, you add them up all the impulses, and finally the output is going to be the sum of all the individual responses. That will be your total response. And in the limit del tau goes to 0, your pulse becomes thinner and thinner, then the approximation will be very fine. So the response will be faithfully the one that will be obtained when the actual x of t is present. So that is the philosophy behind this convolution integral. So that is a strategy that we already used in convolution sum also in the discrete time case. So the same thing that we are going to use it here also. Okay, so this is a very, very important strategy that we adopt here. Because we know the impulse response for a given system, LTI system, we know the impulse response del of t, what is output, h of t. Once you know this one, then you can have number of impulses which are shifted in time and scaled by different amount. See, one impulse is del of t and another impulse is del of t minus let's say tau y, and another impulse is shifted by t minus tau y1, and another impulse is del of t minus tau y2. There are many impulses, and this impulse, this one produces h of tau, and this one produces h of t minus tau y, and this guy gives rise to h of t minus tau y1, and this one is h of t minus tau y2. Like that, there are many responses for each shifted version of impulse responses. Why this is true? Because of the time invariance property. Time invariance property we are assuming. If the input is delayed by certain amount, then the corresponding output also will be delayed by the same amount. And if the input is multiplied by its area, let's say here it is multiplied by x of tau into del tau, then this also multiplied by homogeneity property, x of tau times del tau, because del of t gives rise to h of t. By homogeneity property, a times del of t gives rise to a times h of t. Therefore, whatever you put here, x of tau y times del of tau y, the same thing will appear here also. So del of tau y times x of tau y, like this. So whatever the constant you are putting here, this constant will appear here also. Same constant will appear here. This is a constant multiplying the input impulse. The same constant will appear at the output. That is your homogeneity property. Now you add all this in the left hand side, you add everything. So that is your superposition. So the next one is we are going to apply superposition. If that means superposition means what? X of tau times del tau, del of tau plus del of tau y times x of tau y, and this is a constant multiplied by del of t minus tau y plus let's say x of tau y1 del tau y1, and this is located at, this area is located at del of t minus tau y1 plus x of tau y2 delta tau y2, and then this is multiplied by this area is located at del of t minus tau y2. Now what I am doing, I am essentially doing superposition here. I am adding all the impulses, time shifted and scaled impulses, and if I give this all together collectively to the system, same LTI system, the output will be in summation of individual response. See, this guy will lead to one response, let's say x of tau times del tau times h of tau, the first term, and the second term, this term will gives rise to delta tau y, x of tau y times h of t minus tau y, impulse response. Similarly, the second term also gives the impulse response, and third term also gives the impulse response. You sum them up, all the impulse responses, you sum them up. So any impulse displaced by some amount will also give rise to an impulse response h of t minus tau, which is also displaced by the same amount, translated by the same amount. Now by additive property, that is superposition principle, you add all the impulses. In the input side, the output is nothing but the summation of all the impulse responses. Okay, so that's what we said. That is, if del of t gives rise to a response h of t, then any impulse which is displaced by a certain time interval will give rise to, like del of t minus tau I. This also gives rise to an impulse response h of t minus tau I. So what is the principle which sanctions this property? Time invariance. Time invariant property. This is a time invariant property because the network is time invariant. So any shift in the input will correspond to the corresponding shift in the response. That is what we discussed earlier. And instead of an impulse with a unit magnitude, like here the magnitude is unit, right? We have the magnitude of x of tau y or tau I times del of tau I. The magnitude is scaled by this guy, this constant, del of t minus tau I. The same thing you will get at the output. This constant will not change, will occur here, x of tau I delta tau I times h of t minus tau I. Okay, and this one is the magnitude of the impulse. If that is the input, then you get a corresponding output is going to be this one. So a shifted impulse will give rise to a shifted impulse response, and an impulse magnitude increase by this amount. The output also, the magnitude is increased by this amount. And now here we have the summation of all such things. As I said, there are many impulses, you sum them up everybody. So you put a summation here, x of tau I times del of, this width is anyway constant, you put del of t as it is. Okay, this is a pulse width, pulse magnitude, and del of t is the pulse width, and that width is constant for all the pulses. For each pulse has constant width. Okay, so it is a constant, and the pulses are located at t minus tau I, and where I is equal to minus infinity to plus infinity. You can take n number of intervals. Now what you do is, you make this delta tau limit delta tau to go to 0. If it goes to 0, then you will get more approximated result. Then this gives rise to the same magnitude, but this del of t minus tau I becomes h of t minus tau I. So limit delta tau goes to 0, summation over tau I minus infinity to plus infinity, x of tau I, then delta tau, this is the magnitude, the whole thing is magnitude, but now this del of t minus tau becomes the impulse response h of t minus tau I. Okay, now what is this? This is the input, sum of all the individual time shifted impulses, and this is your output. So in the limit, this entire thing goes to x of t. So if you take x of t, if del of t del tau goes to 0, then this becomes approximately x of t. Therefore if you give x of t to the input to the system, in the output you will get limit delta tau to go to 0, then summation over I is equal to minus infinity to plus infinity, x of tau I delta tau multiply by h of t minus tau y. Now as you make smaller and smaller, then your summation becomes integration. Okay, so as you make del of tau to go to 0 goes to 0, all these impulse are equivalent to the input x of t. So from x of t we will generate this kind of response, this kind of impulses. So you make them closer and closer, approximately that is same as x of t. If x of t is regarded as the series of impulses, and correspondingly this becomes an integration. Therefore both in the left hand side also it becomes integration, and in the right hand side also it becomes integration. So x of t is regarded as integral of x of tau del of t minus tau, because I becomes infinity now, d tau. If we give to an system, then it is going to be x of tau del of t minus tau, then this is h of, wait a minute, hold on, why I put a del of t minus tau, I am sorry, x of tau, then h of t minus tau d tau, and this is essentially x of t. Therefore x of t, if we give to an LTI system, then the output is y of n, and this y of n is nothing but integral of minus infinity to plus infinity x of tau h of t minus tau times d tau. Now here tau is not a discrete point, because we made a delta tau to go to 0. Discrete point, previously it was a discrete point when we started, now it becomes continuous point because delta tau becomes, therefore this delta tau becomes d tau. Okay, if you look at the summation, then this one becomes del tau becomes d tau in this expression, because it is continuous now. Okay. So x of t gives rise to y of t, sorry, this is not y of n, y of t, I wrote y of t, I am sorry, y of t is equal to integral of x of tau h of t minus tau d tau. That is how we obtain in the limit. This integration must last for minus infinity to plus infinity, but in the more usual cases the limits can be further restricted, as we will see later, as we will see at a later point of time. Okay, so no need to do the integration from minus infinity to plus infinity. In other words, given any input x of t, the output can be obtained as you first find out x of tau and then h of t minus tau, multiply x of tau and h of t minus tau, and then carry out the integration between minus infinity to plus infinity. So this is a function of time, right? Your y of t, right? Here t is the function of time, sorry, this y of t is the function of time, and that t is here. So this particular type of formation is usually represented as x of t convolved with the h of t. So this is referred to as convolution, not this one, this one is referred to as convolution integral. The previous case was convolution sum because it is discrete, where we used summation, and here since it is continuous we put a integration, so it is called a convolution integral. So if you convolve two functions of time x of t and h of t, the meaning is this one. So we will come back to the impulse response and the calculation of y of t, but let us spend a few minutes on the meaning of convolution integral. So convolution integral of two quantities, let us say x of t and h of t. That is, how do you write? X of t convolved with the h of t, and this is written in terms of x of tau h of t minus tau d tau. Okay, this is a symmetrical arrangement. We can also write as h of t convolved with the x of t. Therefore, this is going to be h of tau x of t minus tau d tau. So, this particular property is called the commutative property. And this convolution integral is sometimes called a Faltung integral. It is a German word. Before 1950s, people called a Faltung integral. Okay, so this is the German name. So what is involved in this integration? It is very instructive to see physically how you interpret this integration. Let us take pictorially, we will represent this. Let us say this is your some function like this, x of t, and your g of t is like this. Let us say h of t is like this. Now what you need to do? You find from x of t to, you change this variable to x of tau, and this one you change the variable to h of tau. Same shape, because we want to use dummy variable for integration, that's why. So h of tau to h of tau, x of t to x of t to x of tau. Now the next step is fold this any one signal, let us say h of minus tau. Therefore this becomes like this. This is x of h of minus tau, and then delay. Maybe depending on the value of t, it is delayed. Okay, so like this. This is move to the right. So h of t minus tau, by t units you move to the right. If t is positive, then move to the right. So yeah, you have two functions here, x of t and h of t. You would like to find the convolution of these two. What you do is keep one of these fixed as it is, don't change. Okay, this x of t, either x of t or h of t, don't change it. Okay, let us say x of t is fixed. Okay, now h of t is folded. This is my h of t becomes h of tau. I just changed the dummy variable, then this becomes h of minus tau. Fold it along the x axis, sorry, along the y axis. So the four keywords are in this process. The first one is fold, or in fact you can say the first one is change the independent variable. Change the independent variable from t to tau. Okay. The second step is fold any one. Okay, like so in the first step, x of t becomes x of tau. I will put double arrow mark. Then h of t is h of tau, like this you make it. Then fold means h of tau is going to be x of minus tau, or you keep x of tau as it is and then do the folding for h of tau, h of minus tau. This is the second step. And the third step is multiply this is fold, and the third step is delay actually. So h of minus tau is going to be h of t minus tau. You need to consider either both t is negative and t is positive. Both the case you need to consider in this. That is third step. And the fourth step is multiply. Either do this or you can do this also. X of minus tau becomes x of t minus tau. Then multiply x of tau with the h of t minus tau, or you can multiply x of t minus tau with the h of tau. Any one, either this or this, whichever is convenient for you. And the fifth point is do the integration. So there are 5 steps involved in this. So these are the 5 key words that are involved in the convolution. So first change the independent variable t to tau, and then fold, shift. So this delay is also called, people sometimes write shift. So let me summarize here. The first point is change of independent variables. Independent variable, that is x of t to x of tau, h of t to h of tau. Second step is fold. Let us take only h of minus tau. And the third step is shift. H of minus tau becomes t minus tau. And the fourth step is multiply. X of tau times h of t minus tau. And the fifth step is integrate these two guys. X of tau, h of t minus tau, d tau, and the limit is of course minus infinity to plus infinity. So these are the steps involved. Keep this at the back of your mind. We can find out the convolution of simple functions quite easily without going for the mathematics. Okay. Now you can do this approach in 2 ways, either using purely mathematical equation, or sometimes you can go for graphical approach. Okay, so from graphical approach you can find out the convolution of different functions very easily. Now let us look at these limits, these 2 limits. Okay, how these limits can change. The limits are from minus infinity to plus infinity, right? Sometimes for some special cases these limits will change. So no need to do the integration from all the way minus infinity. Okay, so sometimes you need to carry out the integration for a particular range. So by the way, this is the general expression. Let us derive some specific expression for some special cases. And general expression for the response y of t for any given x of t. However, we will consider some special cases. That special cases are like causal systems and causal signal. Causal systems and causal signals. We have already discussed what we mean by causal systems and a causal signal, right? If the system is causal, then an impulse del of, let's say del of tau given to the CT system, and the output is h of tau. So causal system. So for t less than 0, the response will be 0, because the input is occurring at exactly tau equal to 0. Tau is equal to 0. Before that, how can you expect the output? The input occurs only at tau equals 0. Before that, The input is 0 in this region, right? Input is 0 for tau less than 0. In that case, how can you express output? Automatically, the output h of tau is also 0 for tau less than 0. That's what we mean by. So, if the system is causal, then the impulse response must be 0 for negative values of time. Therefore, h of tau is equal to 0 for tau less than 0. Sometimes you can change the variable h of t is equal to 0 for t less than 0. It's after all dummy variable. Now, similarly, if the signal, this is for system, causal system. Okay. Now, look at the integration. In the integration, I will come to the little later, 1 second. Now, let us consider a system. If the signal is causal, then that means x of t equal to 0 for t less than 0. Because of these two restrictions, this convolution integral that you are having here, this convolution integral will change, okay, will be changed. So, because originally it is from minus infinity to plus infinity, x of tau h of t minus tau d tau. Now, this x of tau is 0 for tau less than 0. Therefore, the lower limit is from 0 to infinity, because it is 0, no. Or you can write one second, let me write down clearly. Let us say minus infinity to 0 h of t minus tau d tau plus integral of 0 to, let us say 0 minus, let us say from 0 plus infinity x of tau h of t minus tau and d tau. Now, look at in this case, in this interval, see here the tau is between minus infinity to 0 minus. So, in this range, what is the x of tau value for causal signal? X of tau is equal to 0 for tau less than 0. Therefore, the first integration goes to 0. So, you left with only one integration, that is 0 to 0 plus or 0, no problem. You put either 0 or 0 plus, it does not matter. Infinity x of tau h of t minus tau d tau. Now, let us bring the causal system principle. Causal system. When t minus tau exceeds 0, then what will happen? That t is greater than tau or tau is less than t. That means what? As long as tau is less than t, this is positive. When exactly when t exceeds or t exceeds tau, then it becomes non-causal system. Okay, here tau is a running variable. When tau exceeds, okay, when tau exceeds t, then this h of t minus tau, the argument becomes negative. Okay, when the argument is negative, then as per the definition it is 0, because h of t is equal to 0 for t less than 0. Now, look at this argument. In this argument, from this argument, as long as this t minus tau is greater than 0, then your h of t minus tau is non-zero. The moment t minus tau is less than 0, that is t minus tau is negative, then h of t minus tau becomes 0. Therefore, this integration, this whole integration is valid up to tau equals t. Beyond that, that integration will not change. Therefore, the range of integration is up to t. Up to t. After that, the argument becomes negative and it violates the principle of your causal system. Therefore, this guy becomes integral of 0 to t x of tau h of t minus tau d tau. Okay, so let me write very clearly. Y of t is equal to integral of 0 to infinity x of tau h of t minus tau d tau, and this is for causal input signal. Okay, now y of t is equal to 0 to t x of tau h of t minus tau d tau if two conditions. The first condition is causal input signal, and the second condition is causal system. The LTI system is causal system, so therefore the upper limit is t. So for the special case of the causal system with the causal signal, we need to carry out the integration only between 0 to t, okay, limits 0 and t, not between minus infinity to plus infinity. In particular, for example, we may have an impulse at the origin. We must take that effect into account. So in that case, you put 0 minus. Sometimes no, the impulse is located at the origin. So in practice, the impulse has some finite width. If we expand, then this is going to be 0 minus and this is going to be 0 plus. So therefore in that case, the integration becomes 0 minus to tt, in case if we have any impulse which is located at t equals 0. Therefore it should be advisable for us to start from 0 minus to t x of tau h of t minus tau d tau if the impulse is located at t equals 0, because the impulse has some finite width, no. So the starting point is 0 minus and ending point of the pulse is 0 plus. Therefore you start the integration from 0 minus, otherwise you will miss that impulse, that's why. You know, sometimes the impulses may be sitting at the impulse may be sitting at let's say at tau equals t. Again the impulse like this is the impulse del of tau minus t, this is a tau axis. Now this point is t plus and this point is t minus. So again this integration is 0 minus to, you take up to t plus, therefore you put a t plus x of tau del of t h of t minus tau d tau. So this is your y of t. So this is the final expression for causal signal and causal system. So 0 minus and t plus are taken into account for impulses at the origin in x of t and h of t. If there are no such impulses sitting at the origin and at tau equals t, then you can analyze, then you can always take 0 to t x of tau h of t minus tau d tau, no problem. So no issues. But if you have an impulses present in x of t and h of t, it is advisable to take the limit from 0 minus to t plus. That's how it goes. Okay, so let me stop at this point. The next class I will consider some few examples to illustrate these ideas. Okay, so in the next class I will consider some examples to illustrate these ideas how this convolution integration has to be done. Okay, so let me stop at this point.